So here we're just gonna get started talking about the super duper basics of our solution unit. Just getting to know water and a little bit of vocab. So the top of the first page asks us to draw the Lewis dot structure of water. We're not going to have to do this for very many molecules, but this is our Lewis dot structure. And just to recap, if we were doing this from scratch, I would have to add up the valence electrons that come from those two H's and that O. I would probably connect those H's to the O with single bonds first that use 4 of my 8 electrons, and then I can put the remaining 4 as 2 lone pairs on the top and the bottom. And on your paper you might have drawn it like this, but I did draw it out in that kind of not straight line fashion because it is going to be important as we're talking about water in solutions that we remember its shape, because that's going to affect a whole lot of other factors about water and our solutions. So the shape of our water molecule, the electron and molecular geometry, well, because I have 4 total electron groups around my oxygen, 1, 2, 3, 4, then its electron geometry, the total shape of all of its electron groups, is tetrahedral. In our molecular geometry, where we only see the bonded atoms, I only have 2 bonds, and that might make you think it's a straight line, but with those lone pairs on our central atom, our line is bent. Hopefully that's a little bit familiar. I know it's been a while since we did that, but this bent shape of water is going to be really important for us later and what it does to our water molecule. So the next question asks you, well, why is the density of water in the liquid state more dense than the solid state? And it's kind of weird. Water is one of the only substances that does this. And we still have to review a little bit of bonding stuff to help understand this. Remember, there was this thing called hydrogen bonding that happened when we had H directly connected to F, O, or N. Well, here it's directly connected to O. So we have that hydrogen bonding happening. And keep in mind, this is not talking about the chemical bond, the covalent bond between the H and the O. Hydrogen bonding is the intermolecular force holding separate water molecules together. So if you remember that, then the answer to this question comes back to the fact that our solid water has more stable hydrogen bonds, and those are actually going to be pulling our molecules apart more, as much as it might seem like it would pull them together. Because the molecules can start to slow down, that hydrogen bonding can really start to take over, and it makes these really nice, pretty crystals that we know as ice. But those are more spaced out water molecules than what we see in our liquid water, where we do have hydrogen bonding still occurring, but because the molecules are moving faster, that's only going to be acting on each other occasionally. And so the water molecules are moving really fast, and when they get close, they get pulled a little bit closer, but they're constantly breaking and reforming, so we don't get the same nice crystal structure with all of these big voids in them. But we've got all of these empty spaces in between these water molecules here, whereas we don't over here. So that is why water is actually more dense than solid ice. Now, one of the most important things to know is that water is called the universal solvent. You might have heard that before, but in chemistry now we're going to be able to explore why and how this happens. And it does come back to that structure of water. Water is extremely polar. It can pull apart other molecules that are also polar. So think of magnets. If I have a super strong magnet, it can pull apart any other magnet. So even if you were struggling to pull 2 magnets apart, some of those neodymium magnets, if you got an electromagnet and turned that all the way up, then that could pull the magnets apart with no problem. So because water is just so incredibly polar, it's a super strong magnet, it can pull apart all of these other compounds that are also magnetic. Water basically wins. It can pull apart whatever it wants. It's strong enough to break the other intermolecular forces because it has such strong hydrogen bonding. It's so polar there. And that's kind of sort of answering our question here. Why is it such a good solvent? Why is it able to be that universal solvent when others aren't? And it comes back to the polarity of those bonds. That bent shape And that large electronegativity difference, that large polarity between the H's and the O's, causes the molecule to be very polar. It's a super strong magnet. So the O side of the molecule is super negative, the H side is super positive, and so this magnet can go around pulling apart other polar substances. Now, a couple of other just assorted vocab words that we're going to need to be using as we continue to talk about solutions and learning all of the ins and outs of them are down here at the bottom of the page, and that's really all that we need to do to finish out this podcast. And even though there's not a line there, we are going to define the word solution. A solution is a homogeneous mixture of two or more substances. You might have heard this word before. Generally, we use this to talk about liquid solutions or aqueous solutions. Those are pretty common because it's really easy to get things equally mixed and homogeneously, meaning it's all looks the same. So that's really easy to do in water and aqueous solutions. It's harder to do with our solids, but we can have some gas solutions as well. We just don't see the separate parts of our gases, so we don't experience that mixing as much. But gases, liquids, and solids can all technically be solutions. Now, very important two words to be familiar with. We'll use these a lot. Solvent and solute. These are those two substances, at least, that we have to have in order to be a solution. And the solvent is the substance that the other materials dissolve in. So this is a substance doing the dissolving, doing the work. Water is the universal solvent because it dissolves lots of other stuff. So solvent is the thing doing the dissolving. Solute is the substance being dissolved. So those are our two parts of our solution. We can technically have more than one solute in a solution. We could dissolve salt and sugar in water, and then salt and sugar are our two solutes, but we still will always have one solvent, only one thing that's doing the work, doing the dissolving. And that solvent is generally the thing that is present in a greater amount, whatever you have more of. So if you actually took a whole bag of sugar and you put one drop of water in it, technically at that point, water would be acting like the solute. Sugar would be working to incorporate the water into its structure, and the water is just kind of finding a place to be in the sugar if it's present in the smaller amount. But that doesn't happen very often. Most of the time when we're thinking about a sugar-water solution, we're thinking about lots of water with a little bit of sugar in it. Now, this last word before we get to those electrolyte things is alloy. And an alloy is just a mixture of metals, but this is a homogeneous mixture of metals, which means if it's a homogeneous mixture, it's a solution. So what people don't really realize is that the metals all around you generally are alloys, mixtures of metals, which means they're also solutions. It's one of the best examples of a solid solution is an alloy. Now, we have to talk about these electrolyte things, and an electrolyte is really just a solute, a substance that conducts electricity when it's dissolved in solution. So it kind of makes sense. Salt is a very common electrolyte. Let's go ahead and jump down and define non-electrolyte, because it's just the opposite. It's a substance that doesn't conduct electricity when dissolved. And a very common example of that is ammonia. It does dissolve in water. It is polar, but once we get it in that water, it does not carry electrons around. It doesn't help electricity move, so it is not an electrolyte. Now, weak and strong electrolytes are totally a thing. Weak electrolytes only have a few ions, so they only barely conduct electricity. Strong electrolytes, on the other hand, have lots of ions, which carry more electrons faster, so they conduct more electricity. And we're not even just talking about having more stuff dissolved. Of course, if I put 1 teaspoon of NaCl, salt, into water, it's not going to be able to conduct as much electricity as if I put 2 teaspoons or 3 teaspoons. Salt, NaCl, is a strong electrolyte no matter what. It is always going to break up and carry as much electricity as possible. There are some molecules, even if it dissolves completely, that might just not be very good at carrying molecules, or it might not be very good at dissolving. So, for example, H2CO3 is a weak electrolyte, and we actually show that by showing when it does dissolve, it breaks up into the H ions and the CO3 ions. We draw that with a double-sided arrow because the H2CO3 doesn't completely break up. It doesn't completely turn in to those two products. Some of it is actually going to be staying as this molecule together. And without these charged ions, we can't carry electricity. So the less stuff that dissolves, the less ions we have, then the weaker our electrolyte is. A strong electrolyte would be something like H2SO4. It's a pretty similar looking formula, but because of the bonding and the strength of the bonds, that H2SO4 is going to completely break up. So I have a one direction arrow. There is not going to be any doubt about it. Every single H2SO4 molecule is completely breaking up into H's and SO4s in that water. So it makes a lot more ions than the H2CO3 did, so more electricity can be carried. Now, to finish things out, we have two more types of mixtures that are very similar to solutions, but they aren't actually solutions. The first one is a colloid, which is a mixture, but it's not quite a homogeneous mixture because we have slightly larger particles than can really be dissolved, and they are mixed into what I could call a solvent, something that's trying to dissolve them, and they are going to stay dispersed, but they're not completely dissolved because we can see the Tyndall effect occurring. And what's the Tyndall effect, you may ask? Well, the Tyndall effect is a scattering of light by small suspended particles. So basically what this means is a colloid is some kind of solution type thing that seems like a solution. A good example is milk. It doesn't seem like there's chunky stuff floating around in our milk, but there are proteins and molecules that are not dissolved, that aren't soluble in water, but they're just so tiny you can't see them, you don't feel them when you're drinking it. But if you shine a laser through some slightly maybe diluted milk, then you will see the laser beam as it's passing through the milk because it's scattering that light. If you had something like salt water and you shined a light through it, the laser wouldn't show up, the beam wouldn't show up. You would only see the laser at the laser. I'll show you this in class just so that you can understand this Tyndall effect a little bit better. But if you're curious, you can find lots of cool lasers in lots of different colloids on YouTube if you want to explore that idea on your own and bring a cool example to class. Video, not an actual laser and, colloid. A suspension, on the other hand, is even bigger particles, so much so that it's not homogeneous at all. It is always going to be a heterogeneous mixture with even larger particles than a colloid that can be mixed together, but they don't stay mixed because it's not truly dissolved or suspended even. I kind of think of like glitter in water or sand in water. You can shake it up real well, stir it up real well, and for a while, that muddy water or that glittery water does look pretty homogeneous. But if you let it sit and not move around, then those particles will settle to the bottom. They're not going to stay mixed. It's not homogeneous and it's not stable. So you can kind of see these two words that we're defining here at the end that aren't solutions are different based on the size of their particles. And specified colloid is the larger particles in solution, and suspensions are even larger, as well as how they stay mixed with that solvent. So that's kind of the lines that we're drawing for what is a solution. And like we said before, it has to be perfectly mixed, it has to be homogeneous, even though it is more than one substance in order to be a solution. Anything else is either a colloid or a suspension or something even more special and different. So that's where our notes are going to end. Our podcast is done here. We'll pick up on the next page in class together. Hopefully this wasn't too painful.